Hello students, welcome back. Now let's go to section 3, definite integrals by substitution. Do you all recall integration by substitution? Basically, the integration by substitution is reversed chain rule. Here's the chain rule. Derivative of the outer function and inside stays the same, and then multiply the derivative of the inside like a dangling chain. Three-step process. And then let's reverse it. Let's rename g as y. Okay. In calculus 1, I used to use u, but I'm going to use u for something else in this course for integration by parts. So I'll use y for the inside function in the integration by substitution. So f prime of y of x times y prime of x, replacing g by y. And then y prime is dy over dx, okay, German expression. And then from the second line here, let's take the antiderivative. So derivative of the antiderivative, or excuse me, antiderivative of the derivative cancel each other out, and we get this, integrand only. And here, antiderivative of this right hand side. And then please recognize dy dx times dx, that's just dy. So we get final expression like this. But, come on, this expression is almost useless. Practical method is like this. Is there a composite function inside, and you take y as inside, and is there the derivative flying around? That's a criterion, and that's a recognition. And then substitute y as inside, take the derivative, solve for dx, and substitute everything in, and then resulting integral will become a y integral. Integrate that y integral, and then substitute x expression back in. Such as this problem here. So y is the inside, take the derivative, and then solve for dx, and that's going to go over here. Here we go. Inside is y, take the derivative, solve for dx, color coding will help. And inside, the red part is y, and this blue dx is 1 over 2x times dy. Now, after some simplification, you get a y integral. So calculating that y integral, that's easy, using the power rule. And then after that, plug in the x expression back in, and finally the answer is here. Let's do it one more time. I'm going to take y as the inside. Take the derivative and solve for dr, and then plug it over here. Okay, I decide to use character s instead of y. Okay, that's okay. S is the inside. dsdr is 1/3 r squared, so solve for dr, we get this. Color coding will help. So this red part is s. And this blue part, dr, is this, as is solved over there. And then simplify. The resulting integral is an s integral. So calculate the s integral, and then plug in s equals to this expression back in, and that completes the problem. And you can do this for more complicated problems too. Well, enough time for more, so here goes another. Here we don't have big parentheses, but you take the inside, u as the inside, derivative, and solve for dy, and plug everything in there. Color coding helps. And then after simplification, we get 1/2 1 over 2u. You see, y plus 1, 2y plus 2. Division will give you 1/2. And then that is u to the negative first power, so we get log function. And then in the end, here's the third substitution. How about the next? The inside of this radical will do. And then that's my y. Take the derivative and solve for x. Color coding helps. Substitute all those back in and simplify. You get this y integral. Now over here, I see a lot of students making mistake. That is negative of log of square root of y, like this. That's wrong. Do not look at it as a reciprocal function. Change it to a power function. Then you'll see this is negative 1/2 power. And then use power rule. Previously, we had log function. Why? Because you had negative first power. You see, I didn't use log right here, even though I could have. I changed it into power form first and then log in order to cut down such mistake. So negative 1 power, use log. Otherwise, it's a power rule. Okay, those kind of things are integration by substitution, and that's how you can calculate the antiderivatives. Now, how do we handle the definite integral by substitution? There are two ways to do that, and number one is probably the way most students used to use in Calculus 1. Here's an example problem which you already did just now, as a matter of fact. So let me go quickly. Denominator is another character z, and to take the derivative and solve for dy and plug everything in. And denominator is red, and then dy is blue. And then color coding helps. After substitution, you get integral 1/2 z to the negative first power, so we have log function. Substitute everything back in, we get this antiderivative, and then apply the fundamental theorem. In the final antiderivative expression, plug in the top, plug in the bottom, subtract from the other. Make sense? Complete the indefinite integral first, and then apply the fundamental theorem. This works well in Calculus 1. In Calculus 2, it works okay. Most of the time it works, but not always, I'm afraid. For trigonometric substitutions or things like those, it's not going to work. And some polar coordinates and some parameterization, there are some examples that these things will fail. Now in Calculus 3, this first method will completely break down. So I'm going to use the second method in this class, even though this is not wrong. If you use this successfully for the problem and checks out, then you're going to get full credit. But I'm not going to do it that way. I'll do it more general way that'll work every single time. And then the same method can be applied over to Calculus 3 after some extension. Here's how you do that. Substitution is the same. And then we substitute these numbers as well. Y is going from 1 to 2, right? So y is 1, plug it in, then z is 3. You know, y squared plus 2y when y is 1. And when y is 2, z is 8. So here in this expression, y is going from 1 to 2. After substitution, z is going from 3 to 8. So we get this integral computation, antiderivative, and then you don't really do the last substitution. Just plug in z equals to 8 and z equals to 3, subtract one from the other, and of course you get the same answer as before. This is a second method. This second method always works. So here, complete the indefinite integral first, and then plug the top, plug the bottom, subtract one from the other. Here, complete the conversion to the other integral completely. Complete conversion first, and then plug in the top, plug in the bottom, subtract one from the other. Let's see, do we have some more examples? Okay, how about this? Cosine of theta over 1 plus sine squared. What is your substitution y? It is tempting to take y as this denominator, and okay, then take the derivative. So if you do it this way, y is 1 plus sine squared of theta so derivative is 2 sine of theta times cosine of theta. And then, oh boy, this is not going well. I mean, I see just cosine of theta, not negative sine theta, cosine of theta, and then how do we take care of this sine? Oh, we have a problem. You see, the purpose of integration by substitution is to earn simple integral, but it's getting worse than before. So it's not working out. I have to get something else. What is appropriate? For some strange reason, y is just sine of theta because you see its derivative there. How about the inside? Well, it'll turn out okay. Y sine of theta, take the derivative, solve it for d theta, and then substitute everything in. That's what we get. After simplification, we get this y integral. And all of a sudden, you recognize that this integral is a familiar integral. Its antiderivative is arctangent function. So there you go, and then plug the sign back in, and that's the antiderivative. And then apply the fundamental theorem. Plug the top, plug the sub bottom, subtract one from the other. It works. Difficult problem, yeah, but it works. Now here's solution 2. Instead of completing the antiderivative computation, complete the conversion first. Same substitution, but theta is going from 0 to pi over 2, right? So theta is 0, then sine of 0 is 0. Theta is pi over 2, then sine of pi over 2 is 1. So theta is going from 0 to pi over 2, then y is going from 0 to 1. So this is a conversion in the first line. See, color coding helps. Y is sine of theta, that goes here. And then blue part is d theta. And the cancellation, cosine gone, and we get y integral, and also y is running from 0 to 1 because of this confusion here, because of this conversion here. So you have an arctangent function, plug in the top, plug in the bottom, subtract one from the other. There you go. How about this? This time, conversion only. Okay. Takes a substitution of the inside of that square root. Y equals to 1 plus x squared, and take the derivative and solve for dx. Okay, alright. And then, this is going to be inside, red, and dx, blue, and we're going to substitute that way. Moreover, when x equals to 0, y is 1. When x equals to 1, y is 2. Is that clear? 1 plus x squared for x equals to 0. 1 plus x squared for x equals to 1. So y is going from 1 to 2. In the end, we get this. X is going from 0 to 1, so y is going from 1 to 2. After all this substitution, we have a problem. This and that simplification gives only x squared. What do you do now? Well, remember this? Y is 1 plus x squared. So x squared is y minus 1. And that's how I get this red part here. See? This red x squared is y minus 1. So x cubed divided by this x, so we have x squared left. So how do you take care of this remaining x term? Remaining x vector. Go back to original substitution and take care of it. Now the result is just y integration. And then calculating this integral, that's not too bad. You can use a power rule, you see. Expand out, we have a bunch of power functions, apply power rule, and then apply the fundamental theorem. Plug in y equals to 2, plug in y equals to 1, subtract one from the other, and there goes the answer. Do you have any more problems there? Area problems. Another one there. Oh, by the way, that's the same integral that we considered before. And this kind of problem, do not integrate it from -1 to 1. Same here. Do not integrate from -1 to 1 because you're going to get 0 because of the symmetry. So integrate from 0 to 1 and get only this area and double it. Same goes over here. The details are left to the students, and I'll say this review is now complete. We are done with lesson 1A.